Welcome to the third lecture in this series. So in this lecture we'll cover exceptions and then we will discuss the different mechanisms for handling interrupts, exceptions and also important kernel related work via dedicated threads, which almost all the time are separate threads. So as we have discussed earlier, Intel processors support typically 24 different types of exceptions. So this is for the current version of the kernel. And this is for my processor, which is a reasonably dated processor now. I bought it 4 years ago. But that said and done, I believe the architecture is still more or less like this in 2025. This is the broad structure of the architecture. So let us look at some of the more popular exceptions. So the exception is also known as a trap. So the first trap is divide by zero, which is essentially an arithmetic exception where if we divide any number by 0, especially an integer, the result is infinity and that's not allowed. The debug exception we have discussed that earlier, which is if we set events that are of interest for a debugger, then it stops there, but we'll see there are many debug exceptions, not one. 2 is a non-maskable interrupt in the sense it cannot be ignored, so it is not maskable. 3 is a breakpoint. We have seen this earlier. A breakpoint is basically a point in the code where we instruct the processor to stop. So the moment that program counter is executed, the processor stops and raises an exception, which is trap BP. Again, overflow should not happen. An overflow is an erroneous condition. It's an exception condition. So that is why overflows are explicitly trapped. So that is number 4. And we should not exceed bounds and invalid opcode, device not available. The double fault is an interesting exception. That basically means that there was a fault, an exception. The exception handler started running and then the handler had a fault. So it's a kind of a fault within a fault, but that is truly an exceptional condition. And in many cases, it means that the kernel itself has a bug. So it's better to shut down the system because normally what happens is whenever there is a bug that can lead to a security flaw. Somehow an attacker can get in. So it's a much better idea to kind of shut down the system and restart. So let's look at the divide error in some more detail. So what happens is that we have the IDT table. The first 24 entries are for exceptions. So then what we will see is that we see this x86 trap D that has a number. The number here is 0. So a macro can be used when we are initializing the IDT table to basically say that for this number, this is the code of the exception that actually you get associated with. So this is declaring an entry. Mind you, it is simply reserving space. It is not populating the entry. So for populating the entry, what we will do is that we will again use another macro define IDT entry, which does the population. Here, basically for this exception code, it associates a function that is going to execute some code to basically process the exception. So almost all of these exception kind of events go to do error trap. So this is after, of course, saving the context. So in the entry point, you basically save the context first, and then there is a jump that is made into the IDT entry, because here in x86, especially for interrupts and exceptions, it is populated by software and it's also walked in software. So hardware does not automatically call functions. And the reason is that there are many sub cases and functions also have to save the context and then move on. So it's sort of a smarter idea to let software do all of it. So in this case, we call the function doErrorTrap. So let's look at its arguments. They are kind of interesting. So this regex arguments we have seen before in the previous lecture. It is the set of all the CPU registers. It contains their contents. Then this is a divide error. This is the number of the trap. And this is basically the signal that is sent to the process that has had a divide error. So the signals actually follow what is called a POSIX standard. So POSIX was made long back to ensure that the basic Unix semantics, at least the interface part, is followed by a large number of operating systems such that their internals could be different, but they at least follow the broad Unix interface. So Linux is mostly POSIX compliant. It is not 100% POSIX compliant, but especially with signal names and so on, there is some degree of compliance with traditional Unix, which is POSIX compliant. So the SIG-FP signal is sent, and this is like kind of a sub-message code which says that it happened because of integer division. So next what we do is that this function returns the address of the faulting instruction, which is basically the PC in the user space of the program that was running. So that instruction is also of some value in the sense we would like to find out which instruction actually faulted. In the case of a page fault, it is also important to retrieve the address at which a fault happened, such that that address can be taken, it can be processed, we can see where its data is, and then do appropriate memory management. So the CR2 register is used to store this. So it actually stores the address of the faulting data, right? So error get trap address is for the faulting instruction, and CR2 is for the address of the faulting data. I mean, it's a faulting data address, right? This is an instruction address, and this stores the data address at which the page fault happened. So in this case, the default action is to basically send the SIG-FP signal to the process. In case it is not handled, then something else needs to be done as a default action, which we will discuss shortly. So the question is that, let's say that there is an exception and we go through the usual process of saving, storing the context, and then calling the exception handler, and that looks at what needs to be done. Finally, the question is that what is actually done? So we have seen one example where a signal is sent to the process. This is clearly not for an exception that is very critical. So in that case, the process can then handle the signal as it feels fit. Of course, if the process is not handling, then there is a need to resort to a default mechanism, which in many cases is actually to terminate the process. Another set of exceptions, again, which are not very critical, logs can be written using the printk function. So printk is basically print kernel. So regular printf functions are not available in the kernel, but the printk function can be used to write to the logs of the kernel. So this can be done, so it's not exclusive. So we will see that similar to IRQ actions, multiple exception handlers can be called for the same exception, and they will do different things. One of them could be this, writing to the logs of the kernel. Next, as we have seen in the case of a double fault, which is if there is an exception within an exception handler, then the system itself can be halted. So the kernel can go into a panic mode and the entire system can be halted or it can be stalled. Next, if there is some sort of a math error, let's say for instance, some processor does not have a square root instruction, but the rest of all the instructions are there. In the sense it was compiled maybe for version 10 of the processor, but you are running it on version 9. Something like it's compiled for i9, but you're running it on Intel i7. There could be one of those instructions which the current processor does not support, but terminating the entire program seems a little too harsh. So the right way would be to actually handle the exception. So let's assume that there is no square root instruction, right? And the square root instruction is of this type, where you take EAX, you compute its square root, and you put it in EBX. So what will happen is that is basically the square root of this number that is getting transferred over here. Because we don't have an instruction, the processor will not know what to do, an exception will be raised. But what can be done is that the regular grade school square root algorithm can be run, which of course will be a large function, but that can be done. So at the end of that entire algorithm, the square root will get computed, which can then be stored in EBX and the program can be restarted. So this basically means that unbeknownst to the user process, which is using the square root instruction, the value is being computed. It is not being computed by a hardware instruction because the program is being run on obsolete hardware. Instead, smart software is compensating. It is patching the square root instruction with a software patch. The last is the notify die mechanism, which we will discuss next. It is very similar to interrupt handling, where multiple observers or exception handlers register themselves and all of them are called one after the other in sequence. So this holds here where each event has a set of functions that are interested in it. So an event is basically an exceptional event. So you have every function is a handler. So for any exceptional event, you can have handler 1, handler 2, so on and so forth. So if the right way of handling the exception is using the notify die event, then the notify die function can be called. It will traverse a linked list, which is a linked list of all of these handlers, and call them in sequence. Then appropriate action will be taken. For example, let's say if you consider a machine check exception, one of them would like to fix the state of the processor, whereas the other one would like to log the exception using a print k or some other form of logging. So you can have different handlers that actually do different things, which are sort of similar to interrupt processing, but this is a tad more sophisticated. So what happens is that similar to interrupt processing, where if you would recall, we were returning 3 values, none, handled, and wake thread. In this case, 4 values can be returned. The first is notify done, which means that this handler does not care about this event, but the process of scanning handlers can continue. The other is notify OK, which means that the event was successfully handled, which in this case is the exception event, but we can continue to call other functions, which are other handler functions, down the linked list. So this is not stopping you. This is saying that, look, I handled the exception, but you continue down the linked list, invoke other handlers and let them handle the exception as well. Some cases there could be a notify stop. If this is returned, it means that you stop the process of scanning. This basically means the exception has been handled. Whatever was the exception, that has been handled and nobody else should handle. And notify bad basically means that something went wrong in the handler itself, or in general, in the environment that was sent to the handler, or in the code of the handler, something went wrong. So this is clearly a more serious situation. So instead of calling more functions, there is a need to address this situation. So there's a reasonably flexible mechanism, and notify die is a general mechanism in the kernel, where 4 different status codes are returned for different kinds of situations and scenarios. starting from a don't care to okay, keep scanning, to do not scan, to do not scan, and something wrong has happened. So these are the basic broad ways in which exception conditions are handled in the Linux kernel. So a visual depiction of this is like this, that if there is an exception and multiple handlers have registered themselves with the exception, then we can kind of keep scanning in this direction. We can keep checking subject to these return values that we get. And if let's say it is notify stop or notify bad, then the process stops. Next, what we will discuss is we'll discuss three different mechanisms of how to do deferred work when it comes to kernel work and interrupt processing. So what happens is that when we are looking at the interrupt handler, that has a lot of restrictions, as we shall see shortly. So it can't do a lot of things. And also we don't want it to run for a long time because it's a very high priority thread and it itself disables interrupts for some time. So that is why there is actually a need to do a little bit at the time of processing the interrupt. That is the top half, as we have discussed, and defer the remaining to a later point of time, and that is known as the bottom half. And there are three specific ways of deferral, as we shall see next. So let's first understand what is the need for creating a bottom half handler in the first place. This is primarily because there are a lot of restrictions on what the top half handler can do, which is running at a very high priority. So we'll come to priorities in the next slide. But let's fundamentally look at what it cannot do. So it cannot access user space memory. That is because we don't want it to be associated with any process. So the interrupt handler should not work as if it is doing the kernel work of some user process. It's an interrupt handler. It should just handle interrupts. We definitely do not want it to make any blocking calls, which is the same as acquiring locks. The idea is very simple, that because this has a high priority, it will continue to acquire a lock, which means get access to a critical section of code. But the thread that has already acquired the lock, that will have a much lower priority, yet it will not get a chance to run. Why will it not get a chance to run? Because the interrupt handler is running. It's running but not doing any work. So this basically means that it is repeatedly trying to access a lock and acquire it, but it is not being successful. In the process of that, it is monopolizing the CPU, not allowing anything to run. Most importantly, it is not allowing the thread that currently has the lock to run, and unless it runs, it will not be able to unlock, because any thread that has a lock runs, finishes its critical section and unlocks, which means it needs to be given a chance. That is exactly why we do not allow top half handlers to make blocking calls. Right? Same as cannot acquire locks. They are ideally not expected to raise interrupts. Right? So you are an interrupt handler. Your job is not to raise additional interrupts. Otherwise, what will happen is that this can be a prolonged interrupt processing sequence, right? Where there is one interrupt, its handler runs, then it decides to do something. Either it writes something to hardware, or there is some exception. Because of that, some other interrupt is raised, then some other. So this is not good behavior. So one exception here is an IPI. So an IPI is also an interrupt that a software thread generates. Again, here, the explicit aim is that an IPI can technically be generated by a top half handler, even though that's not the desirable behavior. Of course, we would like to limit the code size of the top half handler and also its execution time overall. We would not like it to be preempted by any kernel thread given the fact that it is at the highest priority. It needs to run until completion. And all the interrupts that can possibly be masked have to be disabled. And a few of the high priority interrupts, they will still be enabled. And in case an interrupt handler itself is interrupted, that's not an issue. That is exactly why we have different interrupt stacks. So if this is interrupt 1, its handler is running. So interrupt 2's handler can also run, no issues. And then once it is done with its top half, the interrupt 1's top half, it resumes and runs until completion. But it is important to note that it's only the top half handlers which are running. No kernel thread is running because all top half handlers have a higher priority than all other threads in the system, barring other top halves. So it's important to extend the discussion that we had to also discuss execution contexts in Linux, where a context is an implicit concept, it is not explicit, but it is implicit enough to sort of give us a clear and crisp idea of what exactly it means. So it's essentially like an execution mode, and mode is a combination of several things, as we shall see. So the simplest is the user context. Regular processes execute within it, and they have different user process priorities, so they simply execute. So that is the user context. Then we have the process context, which is in the kernel. This is for regular kernel threads, which again have a priority, could be a real-time priority or could be a user priority also. So these regular kernel threads may be the ones that were user processes earlier and got temporarily promoted to a kernel thread status, or could be pure kernel threads that do not have any user space association. Then we have an interrupt context that we have just seen. The top half handlers use this. So here there are restrictions and preemption is not allowed. So essentially they run till completion with all possible interrupts that can be disabled, they are disabled, right? So mostly interrupts are disabled, even though not all. But that said and done, preemption is not allowed. Then we have a soft IRQ context, which is an extension of the interrupt context. So here again, the same restrictions apply and no other kernel thread or user process can swap these out. But in this case, the only difference from the interrupt context is that interrupts are enabled. So this basically means that even very low priority interrupts, which would have been disabled here, can actually run here. So they can swap out a soft IRQ thread and then they can run and then the soft IRQ thread will continue. But in any case, it is going to run until completion before any regular kernel thread or user process starts. So it is important to keep these four contexts in mind because they will appear several times in our subsequent discussion. Just to refresh your memory, we have the user context for user processes not relevant in the kernel. For regular kernel threads, we have the process context where they run, the scheduler takes care of them. The interrupt and soft IRQ contexts are beyond the scope of the scheduler, unless, of course, we are looking at a real-time kernel. That's an exception, we'll discuss that later. But they are beyond the scope of the scheduler. So in the interrupt context, the top-half handlers will run until completion with interrupts disabled, barring a few that cannot be disabled. And the soft IRQ context has interrupts enabled, but it is slightly lower in priority than the interrupt context, but much higher in priority than the process context. So the role of the bottom half is clear, that it needs to do additional work that you do not want to run in the interrupt context. The bottom half itself can run, as we shall see, in either the soft IRQ context or in the process context, as we shall see. So Linux used to have different mechanisms, but now they have all been replaced and there are three now. So one are soft IRQs, as the name suggests, they run in soft IRQ context. But again, there is some nuance to this. So we shall see that this is reasonably complicated. It's not always the case. So sometimes they can indeed run in process context. And threaded IRQs that always run in process context. The aim is very clear that we want to minimize the duration of the top half thread because the interrupt context is a monopolizing context insofar as the CPU is concerned, and that is why this is not desirable. So in search of low priority mechanisms, we created the soft IRQ and threaded IRQ mechanisms. But again, threaded IRQs still have a reasonably high priority because they are still supposed to function as bottom halves, at least in spirit. But there is a generic method of just scheduling work, right? So regardless of top half, bottom half, you can just schedule a work as a deferred function call. And all of these have the same broad set of parameters. They have a function pointer and they have arguments. So that is always what you do, that whenever a work parcel is created for deferred execution, all that is needed is a pointer to the function and the arguments that need to be given to that function. So we will refer to this as a work item or a work parcel. They mean the same. So a generic mechanism is known as a work queue, which can be used by all the subsystems in the kernel, including the third-party code such as device drivers. So let's now look at soft IRQs. If you would recall, in the previous slide we had said there is some amount of nuance to a soft IRQ. So let's understand what that nuance is. So consider a traditional top half interrupt handler. So it is also referred to as a hard IRQ as opposed to a soft IRQ, which is the bottom half. But then this is also mentioned in the book that we will always use this terminology for soft IRQ, where all the letters are in the lower case. Even though IRQ, when it is used separately, the letters will be in uppercase. So this is kind of like a standard terminology, and sometimes terminologies do not make a lot of sense logically, but we have stuck to what is used. So the top half, also known as the hard IRQ, runs first. Then if there is a need to defer some work, a soft IRQ request is raised. So we'll see how it is raised, but let's assume there is a way of raising it. Then what we do is that we call the function local bh enable. What that does is that it starts executing these soft IRQ requests, and bh stands for bottom half. So what can happen is that a soft IRQ request can execute essentially the bottom half of this, but it can raise another soft IRQ request, right? So that will immediately start executing. Let me just erase it. That will immediately start executing once this is finished. That can raise one more. So on and so forth. They can keep raising them. And all of these would execute in soft IRQ context, which in a certain sense is not fair. That is why the number of times that this can be done, there's a limit on it. And after that, what happens is that these soft IRQ calls are deferred. If they are deferred, it basically means that they will not be executed right now. They will be executed much later. So we need some method of storage, which we will discuss how it is done. But let's assume when you raise a soft IRQ request, then something is recorded over here. It's like the list of soft IRQs. So as we have discussed earlier, that soft IRQs have a generic character. So they can be raised by other kernel subsystems as well, notably, other kernel threads. Even device drivers can, even though they are advised not to. Then they can also raise soft IRQ requests. So it'll again come to this data store that stores all the pending requests. Once this is done, all of these requests have to be executed at some point of time. So there is a kernel daemon called ksoft IRQD. So a daemon is basically a kernel thread that runs periodically. So it runs periodically. People say it runs in the background. Well, that won't mean much in a formal parlance. What that basically means is once in a while this runs. Essentially a timer is set and once in a while it runs. That's what a daemon means. In this case, K stands for the kernel, D stands for daemon. So K soft IRQD, a standard name. It runs periodically, scans this data structure. If it sees that there is a pending soft IRQ, it executes it. Again, the same thing can happen that we have a soft IRQ, it raises one more, that raises one more. So there are two issues we need to look at. The first is these repeated soft IRQs. And the second is how does ksoft IRQD actually run? So here there is a catch. So I would like to ask the readers to kindly be slightly more attentive at this point. Whenever a soft IRQ executes after a top half, it executes in the soft IRQ context. But when a soft IRQ executes, because it has been invoked by ksoft IRQD, it sadly executes in process context. Because ksoft IRQD is a regular kernel process, so it executes all of these soft IRQ requests in its own context, which is the process context, which means the regular scheduler can schedule them and also preempt them. So they do not enjoy the business class benefits of the soft IRQ context. So they can be preempted, interrupts can come. So of course the same restrictions apply, but the biggest point is that they can be preempted, right? Preemption is allowed. Other kernel threads can preempt them, right? So preemption is allowed, which is not allowed in a soft IRQ context. I mean, in a sense, it is allowed in a soft IRQ context, but only top half handlers can preempt it. Other soft IRQ handlers cannot preempt it. In this case, any kernel thread which the scheduler deems to be fit can sadly preempt this, which means it is running at a lower priority. And that too, it is running in process context. So these are the two methods of running soft IRQs. So a high level critique of the design decision from a software engineering point of view is like this, that if the size of the bottom half, in this case the soft IRQ, is small, then it can immediately run after the hard IRQ and it can run in soft IRQ context. However, if there are too many of these, then they can't run in soft IRQ context, so they need to be deferred and run via the daemon mechanism. Similarly, if kernel subsystems are generating soft IRQs, they will also be executed by the daemon mechanism. In that case, they will not enjoy the benefits of the soft IRQ context, mainly because the context is expensive. So this is a privilege that you are extending to top half interrupt handlers that can just do a little bit of additional work once their core job is done. But you don't want it to be a generic mechanism which is kind of used all the time, which is why with ksoft IRQD you simply run them in process context. Once this is done, these soft IRQ work items keep on executing, and whatever is their logic, that logic is executed. So regardless of how we execute a soft IRQ work item, which, as I said, it can execute in the soft IRQ context or in the process context, we ultimately end up calling the function do soft IRQ. That is ultimately what is called. So the devil lies in the details. So there are two questions that we need to answer. The first is that how is a soft IRQ request raised and what happens within do soft IRQ broadly. So raising a soft IRQ is not very hard. So in the per CPU region, we have a memory word. There are a set of well-defined soft IRQ types. So it is not possible to add a new type. So there are a set of compiler defined or compile time types. Like high soft IRQ is high priority work, timer, network transmission, network receive, block IO, scheduler, high resolution timer, so on and so forth. So this category, for instance, corresponds to a bit in this memory word. If this bit is set, this means that a timer soft IRQ request is pending, and the do soft IRQ function, it pretty much knows where to fetch the work parcel from. So what raise soft IRQ would do is it would simply set the memory bit corresponding to the soft IRQ type to 1. That is all that it is going to do. And then it will place the work item somewhere. What do soft IRQ would do is that it would basically see that the memory bit is 1, fetch the work item and execute it. There are a set of well-defined types as we just mentioned, and each type corresponds to a bit in this per CPU memory word. So all that K-soft-IRQ-D has to do is scan these memory words, find a 1 and execute the work item associated with it, and once it is done, convert a 1 to a 0. So what is very clear here, that there can only be one pending work item per soft IRQ type. So this is why it's not a generic mechanism that consider timer soft IRQ. At any point of time, for a given CPU, only one timer work item can be pending, not multiple. So this is a very simple approach where we have a bit vector stored in a memory word. One bit corresponds to a soft IRQ type. If it is set to 1, it means work is pending. You can take the work and you can execute it. Of course, the support that we have is for a limited number of soft IRQ types. So the flexibility of this method is in question. So extending the previous discussion or continuing it, the main idea is to check for a 1 in the per CPU memory word and then execute the soft IRQ work item. So there is one point that is due. So the fact is that there is a notion of pending work or deferred work. This notion is coming basically because some kernel subsystem is adding something to a soft IRQ, to the soft IRQ database, or it's raising a soft IRQ, which is ending up setting up a single bit. It is setting a single bit in the memory word to indicate that a request is pending. And of course, the reason that this mechanism is restrictive is because for a certain type, only one request can be pending. And also, it sometimes so happens that after a hard IRQ or a top half, the soft IRQs start running in soft IRQ context. But then, of course, if they are creating too many of these, at one point, the kernel says stop, right? So your glory days are over. So no more soft IRQ context. It basically defers all the work. So when it defers the work, we have seen the TIF need reshed flag. The TIF need reshed flag, what it does is that it essentially indicates to the scheduler that there is pending work. So whenever something is deferred and the top half, then a couple of soft IRQ invocations, and then a deferral. This is a situation where some work is being deferred, so the TIF need reset flag is set. So similarly, there are a bunch of other scenarios, similar scenarios in the kernel, where the moment work is deferred, the TIF need reset flag is stored. But clearly here we have seen a very different kind of an execution pattern, where some soft IRQs are executed in a soft IRQ context. But again, we don't want to misuse this facility, which is why for the remaining, they are deferred and run in process context using K-soft IRQD. But again, all of them have the same set of restrictions. So the restrictions don't change. If we were to look at a less restrictive option, then we can look at threaded IRQs, which basically are separate kernel threads that execute the work parcels. So there used to be a mechanism called tasklets. Again, it's not the same as a threaded IRQ, it is different. And a lot of device drivers still rely on them. But threaded IRQs have broadly replaced tasklets in terms of use. They run deferred functions, but the thing is that they run in process context. They are dedicated kernel threads that run at a real-time priority of 50, which is reasonably high. This is not a small priority. This priority is reasonably high, and it is definitely way more than all user processes. So to understand the motivation behind a threaded IRQ, let us look at struct IRQ action again. In this case, we have a pointer to a thread and we have a function. So we are running this thread function using a separate kernel thread. That is the aim. So the aim here is that if this particular handler wishes to run on a separate thread, then you would recall something called a wake thread was being sent. The new thread can be started and it can start to execute this function. So this option is there. So in a certain sense, a threaded IRQ is basically this mechanism where you are specifying a thread and a function. So given the fact that we have looked at threaded IRQs, soft IRQs, let us look at something that is even more generic. This is meant to be used by both kernel subsystems as well as device drivers. And we are clearly not interested in an interrupt context, nor are we interested in threaded IRQs that actually run at a very high priority. So 50 is a very high priority, and anything more than that will make the system unstable because genuine kernel work cannot be done. That is why if we use low priority kernel threads to do the work in a generic and flexible manner, work queues will come in. So if you recall, soft IRQ had a restriction, right? That for a given soft IRQ type, only one work item can be queued. So work queues have no such restriction. The price that you pay is the process context and normal priority. Here again, the core of the function is the work struct data structure, which has exactly the same a function pointer and arguments. This is always the case. You have a function pointer and the arguments. So if we look at a work queue, we see that it is a reasonably complex structure because it is not one structure but actually several. So what happens is that we actually create a bunch of what are called worker pools. Each worker pool has a set of threads and we have a linked list of work structs. So a work struct we just saw, that is a parcel of work. So we have a linked list of a parcel of work. And so we'll talk about the inactive pool later. Let us not think about it for the time being. This is just added for the sake of completeness. But a worker pool is basically a set of threads that are meant to do the job of processing these work structs. And each worker pool has a wrapper, and we have many such pools along with their wrappers, so we'll see what they are for. So you can go to kernel-workqueue.c and also kernel-workqueue-internal.h. So the main idea is like this, that every work queue actually has several pool work queues. So pool work queue is nothing but this structure over here, inclusive of the wrapper, both. So we will see what the wrapper does shortly. But the basic worker pool that you have, that contains a linked list of work items. And every work item is a kernel task that is assigned to a worker thread. So some thread is assigned this task, and the job of that thread is to execute this task and finish it. So what we are seeing is, we are seeing a reasonably complex structure where the first thing, if I were to start bottom up, is there is a linked list of work. What is a work item? Well, a work item, as we have seen, is a function pointer plus its arguments. And this entire thing is assigned to a thread. And the thread will execute this, which is also something that we saw in IRQ action. And these threads are known as worker threads in the context of a work queue. So let us now look at it in slightly more detail, given that the overall concept is kind of understood. Even the parts of it might be vague, but we'll try to clarify everything as we proceed. So let's start from the bottom. So every work struct has 3 fields. So what we do is that we maintain a pointer to a function, right? So this is a pointer to a function which we will execute. So this is my function pointer, and I will give it some data, which is this. So the data as you can see is an atomic long, which basically for long t, let's say it is 64 bits. But sometimes, I may need much more data. So this can actually be a pointer to some structure that stores a lot of data. So all that we are allowed to store here is 64 bits. If all my arguments fit within 64 bits, well and good. Then I can interpret this as just my arguments. Otherwise, I can interpret this as a pointer to a structure that stores all my arguments. So basically, I have a function pointer and I have my arguments. And given that work structs are stored as a linked list, so we have seen this entity before, where this allows us to create a linked list of work structs. So this would be something like this, as is the case in Linux, that it is a doubly linked list. Each entry over here is a work struct. So each work struct represents pending work or deferred work, which is executed later on depending upon the scheduling priorities of the kernel. A worker pool is typically associated with one CPU, and every CPU would have a worker pool where there will be a set of worker threads, right? So a worker pool will have a set of threads whose job is to execute the work items on that CPU. It will have a linked list of work structs, which are all the individual work parcels, and it will have a linked list of worker threads that are idle. So whenever it feels like giving some work, it plucks an idle thread from here, gets a work parcel from here and assigns it to this thread. And then, depending upon the convenience of the scheduler, it is scheduled and the work finishes. The reason for having multiple threads is, and mind you, we are having multiple threads on a single CPU. The reason for this is that a thread may get blocked for some IO or something, because in this case, the threads can actually do a lot of work and there are no restrictions. So if they are blocked, some other thread can take over. That is why we have multiple threads. and every thread is assigned one work parcel. It finishes that, it comes back, it is added to the idle list, another work struct is fetched, an idle thread is fetched, and then they are paired. This pairing between a thread and a work struct is maintained in a hash table, which given a pointer to a work struct can provide a pointer to the thread that is currently processing it. So it essentially maps work items or work structs to the worker threads that are a part of the worker pool. And as I said, every CPU is assigned a worker pool of this type. Where fundamentally there are two kinds of structures. One is a set of work structs, the deferred work, and a set of worker threads which are allotted to this CPU such that whenever there is a need, we can just pluck an idle thread and then we can assign work to it. We don't have to create a new thread afresh. Now let us look at pool work queue, which is the wrapper of a worker pool. So the reason you need a wrapper, this is a standard software engineering technique where, let's say, if you have one object, you have another object that kind of works as a wrapper on top of it. Its job is to control the behavior of the object here and provide an interface to the external world. So this is a software engineering pattern in a certain sense. So if the number of active work items in a worker pool exceeds some threshold, let's call it max active. So what happens is then the linked list will become very long. So to avoid such long structures, because long linked lists are hard to allocate in the kernel because kernel memory is very disciplined. So what is done is it is put in another region known as the inactive works section. And that is a much larger region and it's not a priority region. So all of these work items are put there so that the size of the active work struct still remains within a bound. So this is the job of the wrapper class, which mainly regulates the behavior of the worker pool, as I said, by creating two different lists, one for the active work items and one which is an overflow area. The work queue struct is the apex data structure, which has a linked list of these pool work queue structures, wrappers basically. So this is for the entire system. So for the entire system, it will have these things, and then every single wrapper, there'll be a linked list of those. Some of the standard functions for creating a work queue and working with them are as follows. Create work queue takes the name of a work queue as input, creates a work queue. You can queue work on it, so just give it a work struct. Flush scheduled work will basically try to clean it up by finishing all the work. And there are many kinds of work queues, so there are some which are system wide. So whenever we are talking of a system wide work queue, we are talking of a lot of work, and each of these work queues would basically have a CPU specific wrapper. So this would be one, this would be one, this would be one, this would be one. So let's say if there are 16 CPUs, we'll have 16 of those wrappers, where a wrapper is a pool work queue. So we'll have 16 of these, one per CPU. So some of these work queues are always present because we keep on doing some or other work. Hence, it's a good idea to have some permanent work queues, which are kind of initialized at booting time and kind of remain there. So system work queue is for general system-wide work, high priority as the name suggests for high priority work. Long again for work which takes a long time. Unbound means that it's not bound to a specific CPU, so you can assign it to anyone that you wish. Freezable is for categories of tasks that at any point of time can be frozen. Frozen means suspended and resumed later. Power efficient work. So this is very important in mobile systems, where if you want to do something where we want to minimize the power as much as possible, put it in a separate power efficient work queue. Then what will happen is that whenever a function is processing it or it itself, it can kind of set the processor in low power mode. So there's also one advantage of a work queue, that every single work item or work struct is treated in a similar fashion. So similarly feasible, power efficient, you broadly get the pattern. In addition, there are two work queues per CPU, one for normal priority jobs, one for high priority jobs. So these are all the work queues that are present in the system, where the broad idea of a work queue is actually quite simple, because we have been seeing the same pattern repeat again and again over and over, that we have a bunch of threads and we have a bunch of work structs, where the work structs organize as the linked lists or the parcels of work. And to do something, we just have to assign a work struct to a thread, and what we are assigning is a function pointer plus the arguments. So the central player in this entire story is the function pointer, which we are storing, and that is enabling us to create these wonderful, beautiful, complex structures, which are nothing but nice data structures to wrap the idea of a function pointer. So now that we have discussed soft IRQs, threaded IRQs, and work queues in a reasonable amount of detail, we will finish this lecture. In the next lecture, we will discuss signal handlers.